All righty, look at this. We got folks here. Good morning, guys. Nice to sort of see you, or at least to see your names. Today's going to be our final lecture before exam one. Remember, exam one has been moved to next Monday in order to accommodate the hurricane or tropical storm and all of these other things that have been going on. Today we're going to talk about substitutions in differential equations. We're going to see kind of the last content here from chapter 2. So the last little bit of the class that's going to be focused exclusively on first order equations. Specifically, we're going to see how to change variables in differential equations. And we're going to meet a couple of differential equations, or a couple of families of differential equations, where changing variables, making an appropriate substitution, will allow us to take a differential equation from a form where we don't know how to solve it into a form where one of the methods that we've learned previously applies. I am still kind of getting over that cold, whatever it was, respiratory infection. So I apologize if I'm a little bit soft-spoken again today. The other thing I wanted to do today, I'm working on your study guides, by the way. I'm sorry this hasn't been up yet, but it will be up shortly after class today. The other thing I wanted to do today is solve maybe one more exact differential equation, because we only got to solve one of those together the other day. And I think it would be a valuable experience for us to solve at least one more together, just to make sure everybody's comfy with it. Why is this going so slow? Come on. Having all sorts of strange problems with my work computer. It says down here that it's 9:41 a.m. and things aren't syncing. I don't know what's going on, but hopefully none of those issues will run us aground today. All right. It's a lecture, and today is what, the 8th, I think? Okay. Yeah, the 8th. Now, before we actually get into the mathematics, I'll talk about the procedures for test 1. Then we're going to practice exact equations. And then we're going to talk about substitution. Substitution is section 2.5. Exact equations, remember, is section 2.4. So this is kind of the roadmap for today. If you want the practice here for exact equations, if there's a particular exact equation in the homework set that you want to look at, we can look at that. Otherwise, I'll take an example of my choosing. Within substitution, just while we're kind of putting headers in our notes, we're going to learn about Bernoulli equations today. The Bernoullis are an interesting family of mathematicians, and there were a handful of them: Johann Bernoulli, Jacob Bernoulli, and I think some others. I'm not sure which Bernoulli this particular family of differential equations is named after, but if you're ever curious about kind of the culture of mathematics and you want to learn something interesting about famous mathematicians of yesterday, yesteryear, decade, century, the Bernoullis are a fascinating group of people to study. They're well known for their work in fluid dynamics. If you know how a carburetor works, for example, the work of the Bernoullis is instrumental in understanding carburetors. So, fun side note. But first things first, let's talk about the procedures for exam 1 and study guide 1. I want to be really, really clear about this because in the past there has been some confusion about the study guides, and I don't want that to happen. Okay. So for the study guide, the study guide is basically it's a collection of problems that I think are especially important for you to solve leading up to the test. The study guide is going to appear in WebAssign. So it's WebAssign. And you do need to complete it in WebAssign, but that's not where your study guide grade comes from. You need to write out your solutions. And then you need to, must scan and submit those solutions in Canvas in the assignment study guide 1. Credit for the study guide, like the credit that's in the syllabus, comes from your scans, does not come from completing the thing in WebAssign. WebAssign is just the vehicle for me to get the problems to you. The way you get credit for the study guide, and the study guides in this class are worth a meaningful amount of points. The way you get credit for the study guides is by submitting the scans. Asterisk here. The reason for this is obvious. I've been on the internet long enough to know that it's not all that hard to find places that'll tell you what to type in the box on WebAssign. I want to actually force your hand and make you write out a solution at the very least. And hopefully that solution will be your own, one that you worked out yourself, because otherwise you're wasting time. So the point of the study guide is for you to write out your work, scan it, and submit it in Canvas. And that gives me an opportunity to look at it. That way I can kind of get to know your style. It also gives me an opportunity to give you some feedback on it. And I will do my very best to look through everybody's study guide submissions and get you some feedback as quickly as possible. This means that it's worthwhile to try to get them done somewhat quickly. The study guide is not going to be a very long assignment. It's only going to have a handful of problems. And the sooner you submit your work to Canvas, the sooner I can get in there, take a look, and give you some feedback. This is something you really do want before exam 1, because of course, exam 1, I'm going to be grading your work. It's not a multiple choice test or anything like that. So you really you do want to complete the study guide honestly and submit those scans to Canvas as quickly as you can. Another little note here, the app I recommend for scanning of course, if you have a physical scanner, that's great. Or one of the following apps. Cam Scanner. This is on Android. That's what I use. And the Notes app. If you're on an iPhone, So. And the scans need to be in PDF. Please don't submit a blurry, chopped up JPEG or GIF or bitmap or any of that stuff. Please a PDF. I'm not going to restrict the file types. So it's on you to please just do the right thing here and scan them as a PDF. Cam Scanner will output a PDF by default. My understanding is that Notes is capable of outputting a PDF, although I don't have an iPhone, so I can't verify. So that's the study guide. Any questions about the study guide? All right, probably a problem or two from each section, something like that. You know, just real short assignment intended to allow me to see your work and give you some feedback on it, ideally before the test. The study guide is due on the day of the test. So if you hand in the study guide like 5 minutes before class on Monday, I'll give you full credit for it, but you're not going to get feedback before the test. So it's kind of on you to use your time wisely here, and I recommend getting it done and getting those scans in as soon as you can. That way, there's a better chance that I'll be able to give you some useful, meaningful feedback before the test. So when is this due? Before class next Monday. That's the day of the test. Okay. I recommend handing it in no later than like Sunday. If you hand it in Sunday morning or Sunday afternoon, that gives me, at least Sunday evening to get in there and look at stuff. Of course, if everybody waits till Sunday afternoon to hand it in, then I might not get to everybody's stuff by Monday morning. So I promise I'll do my best. You do your best. The sooner you get it in, the more likely you get good feedback before the test. Last call for questions on the study guide. All right, so I'm gonna say it one more time. You gotta submit the scans. If you just complete the assignment in WebAssign and don't submit the scans, 0 points. If you submit your scans, by the way, one more thing, these are not graded for correctness. They're graded for completeness. I wanna see an honest effort on every one of the study guide problems. As long as you have that there, you're gonna get full credit on the study guide. You make a mistake, I'll give you some feedback, and hopefully you don't make that mistake on the test, but I'm not gonna penalize you for it on the study guide. Now you skip a problem, I'm going to penalize you. So that's the way this works, right? The grade for the study guide is an easy grade. Just get in there and show me what you can do. And don't cheat on the damn thing. If you cheat on the goddamn thing, then you're not going to get the feedback you need. If you hand me a perfect study guide versus handing me a study guide with 10 errors on it, you're going to get the same grade. But if you hand in the perfect, cheap, fake, Quora, whatever study guide, then you're not going to get shit out of it. You're not going to learn anything. So there's absolutely no reason for you to copy answers or use any of the many online tools for hacking through math homework. Please show me what you know on the study guide, and that way I can help you prepare for the test. It's sad, but I've seen many people submit perfect, beautiful study guides and then fucking bomb the test, even though the test has some of the exact same questions from the study guide. Yeah, don't do that. All right. Procedures for the exam. So first things first, the exam is during class time, and it must be taken during class time. This is a hybrid course, not an online course. Exam is during class time on Monday. Which is what, the 12th, I think. there are going to be two mechanisms for proctoring. One of which is honor lock. And for honor lock, you need to use the Chrome browser. So you must use Chrome. This is floating, open. Must use Chrome. So if you don't have Chrome installed, please download and install Chrome on your laptop or desktop or whatever device you're using. And then go ahead and download the most recent version of HonorLock. Even if you used HonorLock like last semester, please go ahead, either uninstall, reinstall the extension, or update the extension. Make sure you have the up-to-date version of HonorLock. Similarly, make sure Chrome is up to date. Chrome, and I'm going to abbreviate HonorLock HL updated to the current version. All right, Santa Fe has been running with HonorLock for over a year, so I trust that most of you have used it before. If you haven't used it before, you're nervous about things, reach out to me ahead of time. Even if you aren't nervous about it, if you haven't used it before, I strongly encourage you to reach out to me or to the HonorLock support people ahead of time to make sure everything runs smoothly. So that's HonorLock. Are there any questions about HonorLock? Okay. The other proctoring mechanism is Zoom. So you're going to sign into a Zoom meeting on Monday. You will come to class, you know. Via Zoom, like normal. Differences here, cam and mic have to be on. And they got to stay on. I'm going to put you in breakout rooms. All right, so I'll create a breakout room for each person. And then you're going to be setting up your phone, right? Zoom, this is going to be on your phone, not on your laptop. And you're going to set up your camera kind of leaning against a coffee cup or something on the side of your desk where I can see your hands, your workspace, your paper, all of that stuff. And you know, the obvious reasons, right? People have secondary devices they keep in their lap. People do all sorts of shitty things. And this is one of the ways I've found to discourage people from doing that. It works well. I know everybody has a cell phone. If you have a technology issue, reach out to me. I can help you get a hold of a secondary device to use for this. But I know everybody has a smartphone. So download Zoom on your phone if you haven't yet. I know probably lots of you are on your phone right now. If you're not, that's great. I obviously prefer you be here on your laptop that we can see a little better what I'm doing. But you need to download Zoom on your phone. And we're going to use both HonorLock and Zoom to proctor the exam on Monday. I've been doing this for 2 semesters now. It's worked great. I haven't run into anybody with tech issues, so I don't anticipate any. But if you anticipate having some technology problems, let me know. Let me know immediately, and we'll figure it out. Any questions about the proctoring mechanisms? All right. Now on Zoom, I'm going to be dropping into your breakout rooms, right? I'm going to bounce from room to room and just check in on you, see how you're doing. Be aware Zoom will be recording you and HonorLock will be recording you. HonorLock will record your screen and your laptop webcam. Zoom will be recording whatever Zoom's camera is pointing at. So your phone's camera is going to be pointing at your desk, your hands, your lap, that shit. So all of those things will be recorded. You may want to be mindful of that before you sign in for the exam. I had a kid last semester leave his big ass dab rig sitting right here on the desk next to him. That was kind of funny. I've seen other even less appropriate things. So don't put me in a position where I may end up being called to testify or some shit like that because you left something in front of the camera. Be smart about this, guys. Finally, and the most obvious thing, where is the exam? How's it going to work? The exam's on Canvas. There are true, false. I think about 4, I think the way I have it set up. There are multiple choice. Again, 4 to 5 questions. And there are free response. I think there's like 6 to 8 of these. So that's the breakdown of the test. The free responses are worth 10 points each. The multiple choice are worth 6 points. And the true false are worth 4 points. Take your time on the true false and multiple choice. I'll let you know some of the feedback that I've gotten on my tests in the past is that my true false are very tricky and that my multiple choice are quite tricky. And the free response are usually not terribly hard. But these tend to be a little bit sneaky. So it's hard for me to force you guys to think critically on a test. On the free response, mostly, I just want to see that you kind of know what to do. But the places where I'm really going to be pushing you to think critically are in the true, false, and multiple choice. And because there's 4 to 5 of them, and each pair of true, false, and multiple choice is worth the same as a free response, it's possible to bomb the exam just by bombing the true, false, and multiple choice and doing okay on the free response. So think carefully and critically. Don't just plow through the true, false, and multiple choice. I can talk to you in office hours if you want about test taking strategies. There are lots of really good strategies for approaching a test, like going through and doing the problems you know how to do first, and then kind of grading the problems as like, medium hard, really hard, and I have no fucking clue. And then going back through the test, 3 or 4 times, knocking out the really easy ones, then the medium hard ones, and so on. But if you want to talk test taking strategies, I can do that with you in office hours. Exams in Canvas. Got the proctoring sorted. Any questions about the test or the test procedures? Okay, and I'll say again, if you don't have like a smartphone that you can use Zoom on, or if for some reason your computer, you're expecting trouble with HonorLock, these are all things you need to talk with me about immediately. We need to get them sorted out. These are requirements for the class. They're in the TAF for the class. But if there is a problem, I want to help you fix it rather than waiting for the day of the test and then just throwing our hands in the air and going, shit, we don't know what to do. Last call for questions on any of the exam 1 related stuff, study guide or test procedures. How do you get credit for the study guide?
You turn in the PDF scan of it.
Goddamn right. Thank you, Ross. All right. I'm sorry. I really appreciate the interaction. Just letting me know that you're there and that you're listening. Everybody heard Ross, right? You get credit for the study guide by submitting the scans. Okay. So I would be happy to look at one more exact equation. I think that would be wise because we've only done the one so far. Are there any exact equations from the homework set that you guys would like to look at? Or would you prefer that I pick a problem? I'm not hearing anything or seeing anything in the chat, so I'm going to go ahead and solve a problem here. Determine whether that's exact. If it's exact, solve it. Let's see. So off the top of my head, so maybe we'll run through a few. Determine if the is exact. If yes, solve it. This one looks like fun. So I have not solved this problem yet. I'm just pulling this out of the textbook. I don't know ahead of time whether it is or isn't exact, but it has some features that I want to discuss with you. So let's do x minus y plus 6x squared. Okay. What's the first thing I should do if I want to determine whether this equation is or is not exact?
Identify the m and n functions.
Very good. So right now, this is not in the form that we're used to seeing an exact equation in. We're used to seeing an exact equation written as like something times dx plus something times dy equals 0. In order to determine if the equation is exact, we need to rewrite it in that form. In other words, we need to find the functions m and n. So we're going to try to put this in the form. We're going to put this into differential form. And identify m of xy and n of xy. In order to do that, we're going to multiply both sides by dx. So I'll get x dy equals 2x e to the x minus y plus 6x squared dy. And then I'm going to pull all of this over to the, oh, sorry, dx on the right hand side. Sorry, multiply both sides by dx. Then I'm going to pull all this stuff over to the left. And I'll write the dx term first. Yeah, dy dx. Right. So I'll pull everything over here to this side. That's going to give me negative 2x e to the x minus y plus 6x squared dx plus x y equals 0. And this is more the way we're used to seeing exact equations, right? Something times dx plus something else times dy equals 0. So what is m and what is n?
M is negative 2x e to the x minus y plus e x squared.
Good. This is our m of xy. And that means this has to be n of xy. So to check if the equation is exact, what do we do?
Integrate.
So if we know the equation is exact, then we're going to start doing some integration to solve the equation. But before we can even approach that mechanism, before we can say, yes, that's how we're going to solve it, we need to check the exactness condition. Does anybody remember the condition under which an equation like this is called an exact equation?
You take the derivative of m with respect to y and n with respect to x.
Good. So I'm going to go ahead and call this equation 1. Equation 1 is exact if and only if, I'll write it in the curly notation, even though I really dislike that. And I want to say one more time that this is it's actually the same condition as something called the Cauchy-Riemann equations, or one of the Cauchy-Riemann equations from complex analysis. And especially those of you who are interested in electrical engineering or any field of mathematics, complex variable theory is the most beautiful thing. What we're doing is the same as finding harmonic conjugates. So this is an exact equation if and only if these partial derivatives are equal to each other. Let's take a look. I'm going to simplify M a little bit by distributing that negative. That's negative 2x e to the x plus y minus 6x squared. So what is dm dy?
+1.
Yeah. I'm differentiating, taking a partial derivative with respect to the variable y. So all the x stuff is treated as constant. This is a constant term. Derivative is 0. This is a constant term. Derivative is 0. This is the only non-constant term when we're thinking of the partial with respect to y. So dm dy is 1. And n of xy, that's x. So dn dx is also 1. Hence, equation 1 is exact. Yay! All right, that means we have something we can mess around with. We can try to solve this equation. Who remembers how to solve an exact equation? What is the first step?
Integrate m with respect to x.
Good. Yeah, that's the idea. So being exact means that the function m is actually df dx. And n is df dy for some function f. And so I can begin working towards finding the function f by undoing this derivative. If m is df dx, then the integral of m with respect to x should give me f up to an additive constant. So thus f of xy is equal to the integral of m of xy taken with respect to x plus some pure function of y. And I think we were calling it g of y. So our first step towards finding the function y that we're looking for is to integrate m to try and recover f. All right. So the integral of the function m here is this guy. So I'm going to integrate this dx. That's integral of negative 2x e to the x plus y minus 6x squared dx plus our g of y. And remember, the g of y here is kind of like the plus c, because f is a function of two variables. When you integrate with respect to one, it's possible that you have a constant term, and that constant term is with respect to the integral. So it's a function of the other variable. Really three integrals in one here. Let's start with this last guy. What's the integral of 6x squared?
2x cubed.
Good. What's the integral of y dx?
xy.
Very good. How do I do this one?
integration by parts.
Yeah, so off to the side here, I know this is easy. This is easy. This requires IVP. So off to the side here, I'm going to go ahead and do my integral. Negative 2x e to the x dx using IVP. This is negative 2 integral x e to the x dx, and the IVP for this, I'll pick u to be x, dv to be e to the x dx, du is just dx, and v is e to the x. So that's our little IVP table complete. And that means that this integral is equal to negative 2 parentheses u times v minus the integral of v du, which is negative 2x e to the x. Integral of e to the x here is e to the x. And then when I distribute this negative 2, it's going to become plus 2 e to the x. All right. So altogether, this line becomes, I'll write it by f again. We have f of xy is equal to this term, negative 2x e to the x plus 2 e to the x, plus the integral of this term. And again, the integral of y dx is xy or yx. And then minus the integral of this. So the x squared becomes x cubed over 3, 6 over 3 is 2. So this is minus 2x cubed. And then we still have our plus g of y. So period. So our first big step done. The first big step is to integrate m with respect to x. And that gives you the function f, which is the main thing we're looking for. Remember, the solutions to an exact differential equation are the level curves of f. What do I do next?
Take the derivative of f with respect to y.
Very good. The other bit of information that we have, and that's why I wrote this down, we just used this information to recover f up to an additive function, pure function of y. The other information we have is that n is df dy. So since I have f here, I can take the partial derivative with respect to the variable y and set that equal to n. The function n was just x. So x is equal to d dy of this thing. Negative 2x e to the x plus 2 e to the x plus xy minus 2x cubed plus g of y. Everybody still with me? The function n is just x. So here I just plugged in. And df dy I get by taking this expression, f of xy that I just found, and differentiating with respect to y, taking the partial derivative with respect to y.
So now you need to set somehow set the x to 0.
Well, we're going to go ahead and calculate this derivative. That's what we'll do first. This is an if and only if. So it's the following line. So x is equal to, if I differentiate this term with respect to y, I get 0. If I differentiate this term with respect to y, I get 0. If I differentiate this term with respect to y, all of these become 0. Use a little arrow here to indicate goes to 0, goes to 0, goes to 0, right, when we take the derivative. So the non-zero terms from this are coming from here and here. And the only one we have calculation to do is here. What is d dy of xy?
Just x.
Just x, right? Because the derivative of y is 1, and the x is treated like a constant. And of course, well, what is d dy of g of y?
G prime of y.
G prime, yeah, very good. And by prime there we mean derivative with respect to y. That's why it's so important that this is a pure function of y. Now you subtract x from both sides, g prime is 0. Therefore, g of y, which is the integral of g primed of y dy, is the integral of 0 dy. And what's the integral of 0?
0.
0, yeah. Sorry, what is this? That's what I want to say. 0 plus a constant, right? I should be careful here. It's an indefinite integral. So this is 0 plus c. In other words, the type of functions who have derivative equal to 0 are the constant functions, i.e. g of y equals c is a constant function. So we're done. F of xy is this thing, and now I know the only part I didn't know before, which was g. It's a constant. So therefore, f of xy is equal to negative 2x e to the x plus 2 e to the x plus xy minus 2x cubed plus a constant. I'm going to go ahead and call this constant C1. Because remember, the idea is that to get the level curves, or in other words, to say what we, did we usually use a constant? Actually, let me triple check something here. Yeah, this is good. All right. So finally, solutions to equation 1 come from level curves of f of xy, i.e. curves satisfying f xy equals c for some other constant c. So our implicit solutions here would be c equals negative 2x e to the x plus 2 e to the x plus xy. I'll call this c2 for now, c2, minus 2x cubed plus c1. And then what you realize is it doesn't matter. I had a quick thought here, like maybe this constant we could have skipped writing it, but it really doesn't matter because I'm going to subtract c1 over and then just call c2 minus c1 some new c. It is a fact, and I'll tell you the reason why I had that hesitation it is a fact that first order differential equations should only have in their solutions one free constant. These are first order ODEs. Exact equations are all first order ODEs. This is the same as saying C is equal to negative 2x e to the x plus 2 e to the x plus xy minus 2x cubed, where C is C2 minus C1. And if you want to, you can skip writing the plus C in this step when you integrate your G's. That is acceptable. Not just here, but in general. It's acceptable to skip this because you'll always end up in a situation like this. So finally, from here, if you just want the implicit expression for the solutions, you can stop. But we're in that rare case where we can actually solve for y, so let's do it. This is the same as saying negative xy is equal to negative 2x e to the x plus 2 e to the x minus 2x cubed, and then dividing through by negative x. You get y equals 2 e to the x minus 1 over x times e to the x plus 2x squared. Minus c over here. Minus. So I subtracted the xy over here, subtracted the c over here, and this should then have a c over x, c times. False. Change that. Yeah, there we go. So from here to here, I subtract the c over, and I subtract the xy over. Everything else stays the same. And then from here to here, I divide both sides by negative x. The sign of this last term doesn't actually matter. We could have left that as a minus, but we did have to change the signs of all the others. Just divide by x, you get this. Divide by x, you get this. Divide by negative x, you get this. All right. Questions about this guy? This is my dog's vet calling me back. I do have to take this really quickly. I'm sorry. I'm actually in the middle of teaching a class right now, so I do need to move kind of quickly here. But yes, I do expect to hear back from his regular vet within I'm honestly surprised it's taken so long, but hopefully within the next hour.
Okay, John, what's your last name?
I'll spell it for you. It's long. P like Paul, F like Frank, E-I-L, S like Sam, T like Tom, I-C-K-E-R.
Okay, what I'm going to do is I'm going to put a hold on the appointment for tomorrow. What is your street address?
2341 Northwest 54th Place.
Okay, and do you have a preference tomorrow, 1 to 2 or 3 to 4?
No preference.
Okay, so I'm going to go ahead and let me just double check one thing. I'll just take one more minute and then I'm going to put a hold on the appointment for, I'm going to put an hour hold on it. If you don't hear back from your doctor in an hour, just call us, tell us that you need another hour.
Okay.
And we will put a hold on that 1 to 2 for tomorrow. That will work. And then you'll call us back. You'll just tell them that you have an appointment on hold for tomorrow, and either yes, you want it, or no, you don't. And I'll go ahead and fill out some basic information on a chart for you. So you have a profile started, okay?
Okay.
Right, so give us a call. It is 10:42. By the time I'm done, it'll be like 10:45.
All right.
So call us back by 11:45 and let us know if you want that, okay?
Okay, I'll do that. Thank you.
You're welcome. Take care. Bye-bye.
All right. Sorry about that, guys. I know it's a nasty interruption. I have to put my dog down, so. Fuck am I doing? Sorry.
Are you all right?
Thank you, Cody. Yeah, I'm okay. It's hard. But we got to do what we got to do. He's sick, and he's made it a lot longer than he really should have. So, it's okay. He was diagnosed with cancer last summer. Okay. Yeah, I'm grateful for that too. Most dogs, when they get a cancer like this, they pass away within a few weeks, and he's made it the better part of a year, and made it past the birth of my son, which is nice. So my son got to meet him, and he got to meet my son. So overall, life hands us shit sometimes, and this went better than usual. We're going to continue though. So that's exact equations. And if you want to see any more work on exact equations, of course, you can come by office hours. I'd be happy to work on some with you there. We do need to talk about solutions via substitution. So we're going to move to section 2.5. Thank you, guys. Thank you. Okay, so there's kind of two families of differential equations that you can solve by substitutions, or at least actually the truth is that there's many families of differential equations where substituting is a really useful trick, but there's two that we're going to discuss in this class. And one of them has a kind of unfortunate name. So I mentioned Bernoulli equations earlier. The other one is called a homogeneous equation. And I call it unfortunate in its naming convention because so many things in mathematics are called homogeneous. Even within differential equations, we have kind of two different things that we call homogeneous. You may remember when we talked about the general linear equation, way back in the first day, I said if the right-hand side is 0, if that input function is 0, we call that homogeneous. That's true, and that's one sense of the word homogeneous, but the other sense of the word homogeneous comes from an invariance. So first a definition. A function f of xy, a function of two variables, is called homogeneous, and that's homogenous, homogeneous, EOUS at the end, sorry. Homogeneous of degree alpha, of order if when you swap x and y for tx and ty, in other words, if you kind of scale the x-y axes, again, those of you who have taken Calc 3 have this understanding of functions of multiple variables. If you kind of zoom in on the input space, you stretch out or shrink the x and y axes to the same amount, right? The same t in both coordinates here. Then the function is more or less invariant under that. Not completely invariant, not in the sense that this is exactly equal to f of xy, but that it's equal to t to the alpha times xy. So yeah, the kind of idea here complete invariance under that zoom would be if alpha were 0, right? If f of tx, ty was straight up equal to f of xy. In other words, if this factor was 1. But if the output from the function kind of scales as a power of the zoom level, that's the way to think of this, then we call the function f of xy homogeneous. A homogeneous differential equation, a first order ODE, which remember is an expression like y prime or dy dx equals f of xy, is called homogeneous if the function f is homogeneous of any degree. Right, so a homogeneous differential equation is a first order ODE, and that's, any first order ODE is an expression like this. And we call the equation homogeneous if the function f is homogeneous. That's all. So first, what are we going to do? The big idea to solve a homogeneous ODE, we substitute either either y equals ux, or the way your book writes it is u equals y over x, or v equals x over y. And these are, you could use either one, and kind of the smarter way of writing either of these substitutions is as y equals ux, or in this case, I would write it as x equals vy. Just because things are easier to work with. Remember, your differential equation doesn't have u's and v's in it when you get it. It has x's and y's. So it's easier to plug in something for y, right, when you're going to make your substitution, than it is to like try to figure out how to rewrite the differential equation like this. The basic idea is that you can kind of think of your variable as being a ratio of the original two variables. That's the big idea. And then after you make this substitution, it's going to involve some like differentiation and swapping in for the differentials. After you make this substitution, you then will separate variables. Either separate variables or integrating factors. Of course, if you can separate variables, you should do that. And I think most of the time, these homogeneous equations yield something where separation of variables will work. So that's the idea. That's the main move here. Okay. So let's look at an example of a function that is homogeneous. The kind of long game here is going to be, you're going to take your ODE, test to see if it is homogeneous, and then you're going to write it in differential form, kind of like we do for the exact equations, and then you'll make your substitution. That's generally the procedure here. So let's see. Now your book also has another idea, another way of thinking of this. And because when we do this, we generally want to rewrite them in differential form. Here's an alternate definition of homogeneous ODE. The ODE in differential form, m of xy times dx plus n of xy times dy equals 0 is homogeneous if both m of xy and n of xy are homogeneous of the same order. And that same order is important. In order for this to work, both m and n have to have the same alpha that pops out. So I want to just check to see if a function is homogeneous so we can get a feel for what that is. And then see if we can solve one of these homogeneous differential equations. Any questions on the definitions here? I'll tell you, when I learned how to solve homogeneous differential equations, we just thought about it like this and then made one of these substitutions. But your textbook seems to prefer this. All of the theorems and stuff are written in terms of this. So I'm gonna go through this kind of from this perspective. But it's the same thing. You can do it either way. First, let's see if we can test a function for homogeneity. And you'll kind of get a feel for what homogeneity says about the algebraic sort of shape of the function. Thinking about the definition, how would I test to see if this function is or is not homogeneous? I'll tell you, this is the sort of question I could ask on a test. This would make for a simple true-false. So we need to know how to test. Well, the definition says if I swap x and y for tx and ty, then the function is homogeneous if I can sort of factor some power of t out. So to check, we examine f of tx, ty, which in this case would be tx cubed plus ty cubed. And then we want to see if this is equal to some power of t times the original function. So this is t cubed x cubed plus t cubed y cubed. And you notice, of course, that both of those terms have factor of t that can come out. So I've got here t cubed times x cubed plus y cubed. And x cubed plus y cubed, that's the original function. So this is t cubed times f of just good old xy. So this function is homogeneous of order 3. Right, alpha here is 3, because when I swap tx and ty in for x and y, I'm able to bring out a factor of t cubed, and then what's left over is the original function f of xy. Are there any questions about what I did here? Okay, so let's go ahead and try to solve one of these. Again, my claim is that if you make those substitutions, either y equals ux or x equals vy, just one of those, you have to pick one to make, then the equation should either become separable or should become first order linear. All right, let's try to solve. The equation x squared plus y squared dx plus x squared minus xy dy equals 0. So m and n are these guys. And as long as those are both homogeneous of the same order, we can approach the problem in this way. So m of tx comma ty is tx squared plus ty squared, which is t squared x squared plus t squared y squared, which is t squared times x squared plus y squared, which is t squared times m of xy. So m is homogeneous of order 2. And n, similarly, homogeneous of order 2. We can check. This is tx all squared minus tx times ty, which is t squared x squared minus t squared xy. And again, we can factor out the t squared. So that's t squared times n of xy, both homogeneous of 2. Therefore, the differential equation is homogeneous. Turns out the two definitions, the definition of homogeneous differential equation and the alternate definition of homogeneous differential equation, they're equivalent. So we can attack this problem by making a substitution. And then the substitution is up to us. We could either sub y equals u times x or x equals v times y. Let's try the y equals ux substitution. The goal when you make a substitution in a differential equation is to get the whole equation rewritten in terms of u and x, no more y's. If you make the other substitution, the goal is to get the differential equation written in terms of v and y, no more x's. So everywhere there's a y, I'm going to write u times x instead. The other thing I need to do is calculate the differential dy. And this follows from the product rule. Since both u and x are variables here, and they are independent variables, I can differentiate just like you would differentiate anything else. This is going to be u dx plus, I'm going to write it, you can write it as du times x, but I'm going to write it as x du just to make it clear. So everywhere there's a y in my ODE, I'm going to write ux instead. And everywhere there's a dy, I'm going to write u dx plus x du instead. Then we're going to blow apart, combine like terms, and see if the result is a separable equation. Hopefully it will be. Let me call this equation here. This is our third equation for the day, right? Equation 3. So subbing this into 3 yields I'll have x squared plus ux squared times dx plus x squared minus x times y is again ux times dy, and dy is u dx plus x du. And all of this is equal to 0. So that's the result of the substitution. We're going to, again, kind of blow everything apart. So this is x squared plus u squared x squared dx plus x squared minus u times x squared multiplied by u dx plus x du 0. And now I need to kind of FOIL these. I need to distribute everything. So I'll have x squared times u dx plus x cubed du. My outers. And then my inners, I have ux squared times u dx, that's u squared minus u squared x squared dx. And then minus ux cubed du. Did I miss a term somewhere? I think this is good. So let me just double check. My firsts are here, x squared times u dx. My outers, x squared times x du, and that x du is what it should be, right? This is x squared. That's correct. All right, and then my inners, minus ux squared times u, ux squared times u, so it's x squared times u squared dx. And then my last, minus ux squared times x du, that's ux cubed du. All right. Now we got to collect all the like terms. So anything that has a dx, I'm going to put together. Anything that has a du, I'm going to put together. Of course, I've got a bunch of dx terms over here. So what do I get with dx's? I've got x squared u. X squared u minus u squared x squared. And of course, all of this stuff. So if I put those together, my dx's, all the dx stuff is x squared plus u squared x squared. I'll just write it out. Plus x squared u minus u squared x squared. All that times dx. And then the du stuff. The du stuff is just x cubed minus ux cubed. And we want to try to clean this up as much as we can. So factoring is a good trick. Anything else that we see, we will do. And as long as I did everything right, it should come out pretty nice. Yeah, okay, everything looks good. Are there any terms I can combine here? Yeah, I've got plus u squared x squared and minus u squared x squared. So what's really left here is x squared plus x squared u, which is x squared times 1 plus u dx. And then from the other guy, I've got x cubed minus ux cubed. That's x cubed times 1 minus u du equals 0. Which is looking pretty good. The outer parentheses here really aren't necessary. I can write this as x squared times 1 plus u dx plus x cubed times 1 minus u du equals 0. And then you stare at this until you see what method to use. Remember what we said at the start of class. Sorry, at the start of this section. After we make our substitutions, what are we hoping to do?
Substitute it back to get the original equation.
Well, I mean to solve. So we said after we make those substitutions, we should be able to solve this equation using one of the methods we know from the past. There's only two methods we know from the past: separation of variables and integrating factors. And this is a separable equation. I think it's the case that your homogeneous equations will pretty much always become separable equations after the substitution. So the hope is that this is separable. So let's take a look. Can I separate variables here? Well, let me try to put all of the x's on the, doesn't matter, x's on the left, u's on the right. All right. So I'll leave the dx term over here. And I'll pull the du term to the other side. And then I ask, can I get all the x's to the left? Yeah, well, if I divide both sides by x cubed, by negative x cubed, or by x cubed, up to you, I'll probably just divide by x cubed, and both sides by 1 plus u, then I get 1 over x dx equals negative 1 minus u over 1 plus u du. I can soak this negative into this expression by flipping the order of subtraction. But the big game here is now to integrate on both sides, right? This is separable. We separated the variables. So the integral of 1 over x on the left, that's the natural log of x. Does anybody know how to do the integral on the right? So I'm integrating here. Left-hand side, I integrate, I get the natural log. On the right-hand side, I have negative integral 1 minus u over 1 plus u. I'll just pop the negative out. How about that? Think back to section 7.4 in Calc 2. This is one of the first sort of rational function problems that you look at there. I'm going to give you 10 seconds to look at that. Holy shit. So LHS is easy. RHS is negative integral 1 minus u over 1 plus u du, which is integral minus 1 over u plus 1 du. Last call for interaction here. Anybody know how to do this?
That's one of the trigonometric functions, isn't it?
Not quite. No, if we had some squares floating around, then we could use some trig sub or something like that. Long division. this is a rational function, and the degree of the top is the same as the degree of the bottom. If the degree of the bottom was strictly larger, then we'd need to use partial fractions to expand it. So anytime you're integrating a rational function, your first thought is exactly what Cody said. Are there any trig sub things I should do here? And those kind of three special cases, really just one of them applies. That's the arctan case. But that would require a u squared plus 1 downstairs. So here, what we're going to do is long divide. We have to divide the top by the bottom. There's a poor man's long division. It's kind of an old-timey joke. Long division without having to write out all the long division. It's not synthetic division, it's even better. U minus 1 is the same as u plus 1 minus 2. Add and subtract 1. So u minus 1 over u plus 1 is the same as u plus 1 minus 2 over u plus 1, which is the same as u plus 1 over u plus 1 minus 2 over u plus 1. So all those tricks from your calculus class, very important here. U plus 1 is 1. U plus 1 over u plus 1 is 1, right? This first ratio here is 1. And then you've got your minus 2 over u plus 1. So the way we do this integral is by rewriting it as 1 minus 2 over u plus 1 du. And again, if you had to, you could do the polynomial long division. I think I posted in your review section in the Canvas modules a few links about polynomial division. I'll check after class and make sure. The first piece here, the 1, just integrates to u. And the second piece would be a little substitution. You would substitute z equals u plus 1, and you'll get a natural log. This is minus 2 natural log of, normally I'd say absolute value, but again, I'm just going to be lazy here, like this. And remember, when we separate variables, we have to give a plus c from one of them. So I'll write the plus c on this side. So that's the integral on the left and right managed. The integral on the left was just the natural log. I didn't even bother writing the integral. We all know that one. The integral on the right required a little long division, and then if you like, a tiny little substitution for this. So the implicit solution in terms of u and x is the natural log of x is equal to u minus 2 natural log of u plus 1 plus c. And then the last thing you would have to do is go back through your substitution. That was the thing Cody recommended earlier. Now we're ready to do that. So if you look at the original differential equation, it was in terms of the variables x and y. There were no u's. All right, it was just given in terms of the variables x and y. So if I want to give a solution to that differential equation, it has to be in terms of x and y. What I have right now is a solution in terms of x and u. So I go back to my substitution. My substitution was, recall, the sub was y equals ux, which is equivalent to saying that u is equal to x over y. Sorry, y over x. Goddamn. Equivalent to saying u is equal to y over x. So now everywhere there's a u, I plug back in and you get your implicit solution. If you can, you solve for an explicit solution. Since we are so short on time, I'm not going to bother with the algebra there. You can do it. So this u is equal to y over x. And you've got minus 2 times the natural log of y over x plus 1 plus c. Now, can you solve this for y? No, no, you can't. So it's not even worth it. This is your solution. You're done. You see this process takes a little while. Of course, when I'm doing this, I'm going through every step very carefully because I want you guys to be able to see every little detail. As you practice these, you'll get faster at them. And instead of taking 3 pages, maybe they'll take 1.5. But that is how you solve a homogeneous differential equation. Rewrite it in differential form, make the substitution, either y equals ux or x equals vy. Re-express the differential equation purely in terms of the new variables. So this is an important step, right? You make your substitution and you get to something like this, where you only have the new variables. That equation should be separable. Separate variables, integrate, and then you're done. The truth is that if we look at kind of all first order equations, there's only a few that we can solve. I can always solve a first order linear equation using integrating factors. I can always solve a separable equation. Everything else, even in first order equations, if you can't separate or if it's not linear, you're in trouble. The only other ones we can do are these homogeneous and Bernoulli equations. Now I'm aware that we are about out of time, right? But I want to show you the very basics of the Bernoulli equation so you can get to it. You need to know what a Bernoulli equation is and the rough mechanism for solving. Remember, these are the 2 families of equations we're learning to solve today, homogeneous and Bernoulli equations. A Bernoulli equation is one of the form y prime plus p of x times y is equal to some pure function of x, we'll call it f, times a power of y. Right, that's it. And n here could be anything. If n is equal to 1, then this is a linear equation. And you shouldn't use the methods of this section on it. You should treat it as a linear equation, use integrating factors. But if n is non-integer, which is allowed, be clear about that. N does not have to be a whole number here. Or if n is not equal to 1, just any other real number, then the move is to substitute. So how to solve? Divide by y to the n. Then sub, your book uses the variable u equals 1 over y to the n minus 1, which is the same as y to the 1 minus n. All right, and that's basically the deal. At the end of this, again, either separate variables or use integrating factors. These you'll sometimes need to use an integrating factor for. So I want to move quickly through one example. That way you have at least seen one. Let's do it. Solve x times y prime plus y equals x squared y squared. Of course, in place of y prime here, you could be writing dy dx. Doesn't matter. This is our Bernoulli equation. Here, n is equal to 2, right? Oh, wait, yeah. So is this in the form of a Bernoulli equation? Let me first ask that.
Not quite. You need to divide everything by x.
Very good, right? We need to get the y prime to have a coefficient of 1. So that's my first step. Oh, sounds like our contractors are here. Y prime equals, sorry, God damn it. So this is equivalent to saying y prime plus 1 over x times y is equal to x y squared. Now this looks like a Bernoulli equation. N here is equal to 2. So I divide through by y squared. I get y prime over y squared plus 1 over x times 1 over y equals x. And then we're going to substitute u equals, I'll write it like this, y to the 1 minus n. N here is 2. So that's u equals y to the 1 minus 2 is y to the negative first. Now, I need to get y prime swapped into u prime stuff. And of course, the implicit thing here is that y is a function of x. So maybe I'll rewrite this in terms of the Leibniz notation as 1 over y squared times dy dx plus 1 over x times 1 over y equals x. And then we're going to calculate du dx using the chain rule. Du dx, I take the derivative here, right? And now what we're doing is we're really implicitly differentiating. Du dx is -1 times y to the -2 times dy dx. We want to find a way to make this substitution work in here, meaning I want to get rid of all of the y pieces and replace all the y pieces by u pieces. And there's a bunch of ways we can sort of go about this. Let's first observe that 1 over y squared is u squared. Dy dx, let's deal with that first. So this is the same as saying du dx is equal to -1 over y squared times dy dx. So that's the same as saying negative y squared du dx is equal to dy dx. So here for dy dx, I'm going to replace it by negative y squared du dx. So I have negative y squared. Oh, sorry. 1 over y squared times negative y squared du dx, that's dy dx, plus 1 over x times 1 over y. Well, 1 over y, that's u, right? U to y to the -1 is same as 1 over y. So this is 1 over x times u. And then on the right-hand side, I still just have x. My independent variable x isn't affected by the substitution. We clean everything up as much as we can, and the result is a nice linear equation because the y squareds go away. So 1 over y squared times negative y squared is -1. So this is equivalent to negative du dx plus 1 over x times u is equal to x. And then I can divide through by the negative to get a sort of linear equation in standard form. There it is. This is a linear equation, order 1, in standard form. So you want to check if it's separable. If it's not separable, then you need to use integrating factors. I don't believe this is separable. You could add this over here, and then you'd have, but there's no way to like get the factor of x out from these pieces. So from here, you would solve using integrating factors, and I'll leave it to you to do that. So from here, solve integrating factors. And at the end, replace the U's. With Y stuff. All right. I know we lost time while I was on the phone with the vet there, and I know that that sucks. So what I'll do is I'll go ahead and I'll record a video of me finishing this up, post it, maybe one more example, and I'll get that posted to the announcements for you guys. It'll go in the same place the link for the Zoom meeting was this morning. Also coming up soon, your study guide, that will be up within the next few minutes. I appreciate your patience with me today, guys. It's a weird day, so thank you. Please work hard on that homework. If you have any homework that you need extended, submit an extension request. I usually grant them without any sort of issues. Prepare hard for the exam. Remember, to get credit for the study guide, you need to scan and submit your work. Test is on Monday. If you have any questions or concerns, you can canvas message, email, come by office hours, all the normal stuff. Anything you want to ask in parting before we sign out for the day? Alrighty, then I'm going to go ahead and end the meeting. What sections are the tests covering? So the sections from the syllabus. If you look in the syllabus, the test covers 1.1, 1.2, 2.2, 2.3, 2.4, 2.5, and 2.1. So the test covers all the material from weeks 1 and 2. All right, any other urgent questions before we end the meeting? That's very sweet. Thank you, Miguel. All right, guys, I appreciate your kindness. Have a good afternoon. If you do need any help, remember you can come see me in office hours or email Kim's message. Take care.